How to design a drone. Let's do this. Hello everybody, I am Nick the Naval Architect. We call them Autonomous Surface Vessels, ASV, or just drones for short. But more to the point, how do you design one? Just look at any drone on the market, and you'll notice they look different. These are not like regular ships. They're smaller. There's no place for people on board. There are all these strange antennas on top. Drones are different. And that translates into different challenges, new design quirks. So how do we handle these differences? What are the secrets to designing a drone? Well, we start by understanding the application. The main advantage behind drones lies in their low cost. Drones work best when we're talking about simple, single-purpose missions with a longer timeline. For example, drones found a niche in survey work. Over 72% of the ocean remains unmapped. And that's because it's really expensive to operate a 300-foot-long survey ship that is just full of crew, scientists, and equipment. All of that for the boat to just flip on its sonar and slowly troll across the ocean? Well, now you know why most of the ocean is unmapped. But for the cost of a single NOAA research vessel, we could afford an entire fleet of survey drones. After all, it's nothing more than a sonar, a propeller, and a transmitter to beam that information back to land. And drones can achieve more than just run a sonar. They can measure water currents, collect samples, perform reconnaissance, blow up destroyers, aid in aquaculture, and many more applications. The common theme for all of these drones is that we keep them simple and small. Ideally, the drone is only going to perform a single mission at a time, and that simplicity is the key to keeping the drone cheap. And remember, above all else, cheap is the main advantage behind a drone. So the first problem to look at, stability. How do we keep the drone upright? Better question, do we actually need the drone to stay upright? Most of the rules and standards for ship stability derive from protecting people on board. That's the main reason that we have stability rules. We devote a lot of effort into limiting the ship's roll. Because if a ship rolls all the way over to 45 degrees, people are going to fall and get injured. Objects are going to fly across the room and hit people. Bad things all around. And you'll notice I'm talking all about the people. The ship itself probably doesn't care if it's rolled over to 45 degrees. But people, they break much easier than the ship. So let's look at this again. No people means that we can throw out most of those rules. For example, most ships come with a myriad of openings on their main deck. We're talking about doorways for the people, air vents to get oxygen down for the people and the engines. All of these openings are called down flooding points, because if they ever go underwater, the ship is going to flood from the top on down. Now, conventional stability rules, they invest a great effort to ensure that those openings will always stay above water. But this is not the case for drones. We can build drones more like a submarine. Seal up all those hatches. Even if we're talking about engines on the drone, we can temporarily seal the air vents if that drone goes underwater. So drones can really embody a watertight design, which makes stability far less critical. That said, the small size of a drone does present some new challenges. The drone gets smaller, but the ocean did not. Your typical drone is only 20 to 30 feet long, 6 to 9 meters. But it's going to be facing waves that dwarf it when it's on the open ocean. The drone will capsize. It's not a question of if, it's a question of when. It just takes one unlucky combination of waves for the drone to completely flip over. We guard against this by designing most of our drones with a self-righting capability. Self-righting ensures that no matter what, the boat is going to return to an upright position. There are no machines required for this, no technology. Self-righting is a capability that comes purely from careful design of the drone hull shape. We start by creating a very low center of gravity. Keep it very low down. But the real magic happens in the reserve buoyancy. This is the section of the hull that is currently above water. And if we flip over, what happens when that now enters the water? First thing we do is ensure this entire hull stays watertight. Top and bottom, it's all going to keep the water out. As that drone rotates around, we include large buoyant structures on the top. These might be tall, watertight deck houses, or a flotation bag on the top of a large arch. The key principle is that these structures have to be tall. In normal conditions, these structures are going to stay out of the water. They don't do anything. But if the drone capsizes, all of that goes underwater and turns into extra buoyancy. It ensures that the drone can't find a stable resting spot when it's upside down. Its only choice is to flip back upright. Now, this is not easy. Drones don't naturally tend towards self-righting. We need to be very careful in our design work. To get this right, naval architects will simulate the drone stability and check it on the computer before we ever build the real thing. When we're simulating stability, we look at a graph called the righting arm curve. That's the graph on the right side of your screen. Naval architects, they get a lot of information from this graph. For self-righting, the main thing we need to know is if the curve goes negative. On a conventional ship, the curve starts positive, and at some critical angle, things swap around, the curve drops below and goes negative. That's the highlighted red region in this graph right now. A negative curve means that the ship wants to be upside down within that range of angles. Negative stability. And if a conventional ship were to capsize and rotate into this region, it's going to stay capsized. The classical strategy for stability worries about that crossing point from positive to negative, and we try to push that crossing point as far out into heel as possible. We want to make sure that the ship never actually gets to that crossing point. But with a self-righting ship, we do it a little bit different. The graph on your screen now shows a GZ curve for a self-righting drone. And you'll notice that region of negative stability, it just does not exist. In a self-righting ship, the curve is always positive over the entire range of heel angles, all the way from 0 to 180. No matter how far you roll this ship, it is always going to want to go back upright. And working with a naval architect, we'll be able to tell you that's going to happen before you ever build the first drone. Now, ironically, the biggest problem with self-righting does not come from capsize. It comes from the machinery, especially any fuel-guzzling engines. Those lumps of metal, well, they were designed to work upright. So we need to create several special adaptations to ensure that when the drone flips over, the engine still works again by the time we get back upright. In general, the strategy here is to shut down the engine if we capsize. There are several devices that then protect that engine, ensuring that we can restart it when we're back upright. First off, we're going to need some stronger bolts to secure the engine. Most of the time when you mount an engine to a ship, those bolts, they're not designed to completely suspend the thing upside down. So we got to make sure we protect that. Then we look at putting in a cutoff switch, something that's going to detect when you're going upside down and stop the engine from running. Otherwise, you run into the problem that the lube oil is now draining to the wrong place and it's not protecting the engine. Things can start to overheat. Then we have to look at the air. The engine pulls in air from the exterior vents. Well, if you flip upside down, those exterior vents are now a down flooding point to let in water. So we install special valves that are going to close in the event of a capsize. But don't forget, the engine has a place where it sucks in air, and then an exhaust where it gets rid of the air. So just like with the air intake, we need to close that exhaust when it goes underwater. Naval architects know solutions to each of these problems. The trick comes from recognizing the problems in the first place. And that's why you need a naval architect who's trained to think about all of this system integration. We look across different disciplines of engineering to understand how that self-writing is going to create new requirements on different mechanical systems. Let's talk about power management now. Preparing for the long haul. The biggest challenge with drones comes from power. Now sure, you're going to find plenty of them that can get by with nothing but a battery and an electric motor. They can last for a few hours, maybe a day. But for long endurance missions, the battery doesn't cut it. We can't just supersize the battery, that adds too much weight. So when we're talking about long duration and storing massive amounts of energy, we need to get more efficient and more creative. And there are two major solutions. The first one is engines. Engines offer the more predictable option, and we tend to like predictability. When it works, the engine always provides reliable power, matching all of our needs. One example of this is the drones designed by Chance Maritime. But those engines also introduce a lot of complexity, potential points of failure. So we can't use the engine as the sole source of power. Because remember, the computers and the controllers on the drone, they all require power. And if all of our power is coming from the engine itself, well, if we lose power, we lose communication, and now there's no way to restart the drone. Nothing is listening for the restart command. So even when we're using engines, expect to have a backup power source, either a generator or a large battery setup. Plus again, that engine requires air inlets, outlets, cooling. Those all turn into through hulls, holes in your hull. Every hole is a point of potential flooding. It's a risk that we have to consider. So in short, yes, engines do work great when they work. But if anything goes wrong, we are going to face limited troubleshooting options when we're talking back on land. That means that even with the engine, we need to build in extra redundancy. Multiple engines, spare generator, batteries. It's not as simple as it looks initially. Your power system starts to get a little complicated. Well, if you don't like that, the second option is renewable energy. Harvest power from the environment itself. Now this tempts a lot of people. They think, oh, that means unlimited power. I can do whatever I want. But here's a little note of warning. The sea doesn't really care about you, and it's not going to cooperate with your power needs. There are three main sources if we're talking about renewable power: wave, wind, and solar. Now wave power is the most abundant, but it's very difficult to harvest. There are no commercial off-the-shelf options. You can't just go down to Acme Wave Company and get a wave generator. So wind is the next option. We see this most often as sail propulsion, with the sail drone being a prime example. When we're looking at sail propulsion, that can provide both propulsion and electric energy. Many of these drones still include a propeller that's driven by an electric motor. The real advantage here is that if the sail is pushing us forward, we can now take that propeller and use that motor in reverse. The propeller acts like an electric generator, slowly recharging the batteries. And that's how wind tackles the power of propulsion and all of our onboard electricity. Of course, sails only work when the wind blows. So we come to option number 3, solar power. This is favored for its mechanical simplicity. If you look at a solar setup, there are no moving parts. That seems like a great idea. But solar power really depends on the environmental conditions. Your average solar-powered drone only contains a battery to last 1 to 2 days. So in terms of power management, you're going to need sufficient solar energy every single day. You need to be recharging that battery every day. If we're looking at that kind of daily dependence, it asks the question, how big of a solar panel do I need? Now you might think this is easy. Just go look up the average solar output and size your panels. But in this case, you can't rely on the average. average means that half of the time you're getting less than you expected. Well, if you need that power output every single day, you can't be suffering half the time. So we need to size our solar panels for the darkest, cloudiest days in the year. If our drone is operating near the equator, those dark days are still pretty abundant amounts of sunlight. But if you're all the way up in the northern latitudes, winter is a different story. That brings very scant sunlight and lots of cloud cover. In those scenarios, a solar panel might only produce 20 to 30% of its rated power. Your location on the planet dictates the viability of solar power, so you have to be very careful about where your drone is going. Just like with engines, when we look at renewable energy, there are pros and cons to every single option. And just like with engines, the recommended solution is that we install a combination of different power options. Engine plus sail, sail plus solar, or even solar plus wave. The trick is to find a combination of the lowest cost and the lowest weight, because remember, extra weight adds to the power requirements. This does really take some careful planning, studying the local variability of your renewable resources, but when it's done right, you get a situation where the individual power source is small, but the collective whole of all of your sources offers abundant and reliable power. What to do when something breaks? Because if it breaks on a drone, you can't fix it. You are still stuck back on land. And things do break at sea, all the time. Take the example of the motor vessel Dali with the Baltimore Bridge here in the USA. They only had a momentary equipment failure, but that was enough for the ship to lose control and create a massive collision. When we're thinking about equipment failure, we need to think about the risk of the damage our drone can do. This isn't so bad if we're talking a small toy that only trolls around in harbor. Worst case scenario, you've lost a small, cheap drone. And small toys can't do much damage to any surrounding property. They don't make much of a battering ram if it's something only this size. But for the long endurance drones, we can't really afford to lose that drone. That costs a lot more than a toy. If you're talking about a 40-foot long or 12-meter long drone, that thing gets pretty expensive. So as we expand into these larger and better drones, fault tolerance becomes critical. Your average manned vessel comes with plenty of fault tolerances. Think about all of the fuses on a ship electrical system. These are a great idea. If something goes wrong, the fuse blows, protecting the rest of the system, and it isolates the problem. Now just fix the problem, replace the fuse, and you're back and going. Very tolerant to faults. Except, how do you plan to do that on a drone? Remember, you are not there. You can't touch the fuse. Most drones are going to employ redundancy to get around this remote problem. If a system goes down, you don't try to fix it, you just turn on the backup. That's especially important when we talk about communications. If we lose a communication link, we lose the drone. So we're definitely going to have multiple ways to talk with our drone. And when we're talking about small electronics, this redundancy makes sense. It's relatively inexpensive to add a second GPS receiver. But if we start talking about larger systems, that becomes more complicated. Do you add a second engine? What about your electrical system? Do you need a second generator? So let's look at that example of redundancy on an electrical power system. Do we build a completely redundant power supply? Double the electrical wires leading to every single instrument and device? Well, first off, that just doubled the cost, making things very expensive and very complicated. If you think about a redundant power system, I need some way to keep that backup power isolated, because otherwise, whatever fault killed my primary power might bridge the gap and do the same to my backup power. So now we need a way to connect our backup power to all the systems while keeping it disconnected normally. But we also need a way to switch from primary to backup power. Well, normally those switches require power sources themselves. So now I have a tertiary power system just to power the switch from my primary to my secondary. Wow! That is just a lot of switches and wires and a lot of complexity. Aside from the cost, more complexity adds to your risk. It means that there are more things that can break. So instead, most drones don't come with complete full redundancy. If something breaks, the drone is going to switch to a recovery mode. At that point, we don't expect the drone to have the full capability to continue its mission. We're just trying to get it to return home safely. Recovery mode might mean something simple, like a radio beacon, so that we can go out and find the drone. Or some drones might use a reduced propulsion system that allows it to limp home. We don't have a fully redundant engine, we just have a backup thruster on a battery. The details of disaster recovery, they change with each drone, depending on the systems on board. Most of the drones these days can still continue with one or two minor faults, but they're going to run for home if a major fault happens. But what if we have two major faults? Well, now things don't look good for our poor little drone. I have to admit, when it comes to drone design, fault tolerance still needs improvement. The next major advancement that I really want to see is self-repair. Show me a drone that can change its own fuses. Now, I do see some nascent signs of this already. Some operators equip their drones with cameras for self-diagnosis. For example, I saw one operator, they have an underwater camera that is pointing at the propeller. That is really critical when you're diagnosing your loss of propulsion. Did you lose power, or is the propeller just clogged with seaweed? That little camera solves this problem. So we still have a ways to go, but we are working on solutions. And I really do look forward to seeing the next step, when a drone would contain its own internal repair robot. I think that capability is going to enable a lot of trust for larger drones and better autonomous operation. Let's wrap this up. Drones play by different rules. Their small size and their challenging power requirements, that creates a different philosophy when it comes to ship design, different problems to solve. And some problems still suffer from imperfect solutions, like fault tolerance. But that's really the beauty of the design process. We try different solutions, which help us narrow down the exact problem that we're trying to solve. The strength of human imagination can envision a solution to nearly any problem. And as USVs and drones continue to evolve, their story is going to be the story of creating a clearer definition, a better understanding of the problems that are associated with drones. Each drone that we see out there is a step towards that clarity and progress towards the perfect design. Thanks very much. I am Nick, the Naval Architect.
Thanks for watching. I hope you liked it. What is ship design to you? Because my job as a professional engineer is to take your understanding of ship design, that general goal, and turn it into technical specifications to make it a reality. So check out the website and let's see how I can take your dreams and make them possible. Thanks very much.